Our next speaker is Dr. Greg Flach. Greg is an advisory engineer at the Savannah River National Lab. Over the past 15 years, he has performed numerous subsurface flow and transport analysis for DOE performance assessments of waste tank closure, solid waste disposal, and solid radioactive waste disposal. He currently supports performance assessments of the Savannah River Disposal Facility, E area solid waste disposal facility, and F area and H area tank farm closures through porous media transport simulations and material degradation analysis. He previously supported RECRA and the circular groundwater cleanup activities at the site and developed the simulation software and models for nuclear reactor thermal hydrology systems. Greg earned his PhD in mechanical engineering from North Carolina State University. He received the Department of Energy's Secretary's Achievement Award in 2013. Quite an accomplishment. Welcome, Greg.
Thank you, Ming. So Ming and the committee asked me if I could pull together some of my lessons learned from my experience with performance assessment modeling. So I've done that in this talk, and I'm going to touch some on software qualification, but I'm going to actually spend more time on the broader topic of model verification. So next slide. So the one of the, I guess, the upfront points I want to make is that, you know, models and analyses are more than just codes, and therefore when we're talking about quality assurance for an analysis, it's more than code QA that we need to deal with. And next I'll kind of draw a distinction between quality assurance approaches and what I call quality control approaches, and make the point that really both of these approaches are complementary and needed to ensure a sound analysis. And then I'll also give some of the risk and remedies that are involved in both techniques. I've got a few examples to share, and I'll summarize my thoughts, but then hopefully some of the folks in the audience will step up and share their own experiences and lessons learned on the model verification topic. So next slide. So a typical risk in performance assessment analysis revolves around some sort of numerical simulation code. I mean, that's not necessary, but in this computer age, that tends to be the situation. So I've started off this little graphic here with a block called code, highlighted in yellow in the middle. That's we'll start off at the center of our risk or PA analysis. And then I've drawn several other components that come into play into a typical analysis. And the first thing I want to assert here is that when we're talking about software, it's more than just a code. It's also the code with its documentation. And so when we're talking about software QA, I think properly we should be talking about not only the code, the binary executable code, but again, the documentation that goes with the software. So I've highlighted those two boxes in green. And similarly, if we're talking about a numerical model, it's not just the code, it's also the input deck that feeds that code, and those two things together comprise the numerical model. And of course, the numerical model is really not just the only part of the model. Underlying that numerical model is a mathematical model, and behind that is a conceptual model, and obviously there's data sources that feed into that mathematical representation. So if we want to talk about sort of an overall model, it really encompasses all those elements: the concept, the data, the input to a numerical model, and the numerical code, say, itself. And then beyond that, if we talk about the entire risk or performance assessment analysis, we're also talking about outputs from codes, potentially some post-processing, and that ultimately leading to results that come to a decision. So the overarching idea here is quality assurance must address all of these elements of an analysis if we're going to reach a sound decision. So next slide. Okay, so a little bit on quality assurance versus quality control. So the main idea here is that quality assurance is process-oriented, and its goal is to prevent a defective product. Versus quality control, it's product-focused, and its aim is to detect the production of a faulty product. So the idea is if you're in the business of making widgets, quality assurance would be the steps that you use to develop a sound manufacturing process and all the steps you use to give yourself assurance that any future products produced will be sound and not faulty. Versus the quality control measures would be you standing at the end of the production line, and as the widgets come off, you're waving your wand over them or whatever, testing each one individually and detecting whether there's been a flawed product produced. And so I'm going to really apply these two concepts now to a PA analysis. Let's see, next slide. Okay, so let's start off with the QA topic. This is most properly applied to software, where the idea is you've got a general static capability that can be well tested sort of once and for all, as it were, so that once the software has been qualified, then you have reasonable assurance that any future products that come out of that software will be valid, not be defective. And so in order for this effort to be worthwhile, it needs to be something that's fairly established code and has general capabilities that will come into use many times into the future. Okay, so kind of just listing some of my lessons learned from my own personal experience. If we want to talk about software problems, in my experience, it's input errors and misuse of codes that have created more problems for me than actual errors in the binary coding. And for me, it's often been an issue with functions in the code that are ambiguously, obscurely, or even not documented. Just a couple other things, in my experience, developer-only testing, and me being a developer, I'm guilty of this. If the only developers have tested the code, it's probably still got problems that will be quickly identified by the first or second user. So let me give an example of a documentation issue. Next slide. This goes back quite a few years, but when I just started using, I think, the PoreFlow code, we discovered an issue with the retardation coefficient. So in the upper left here, I've got the conventional definition of a retardation coefficient. This is actually the only way I've seen it defined or used in any other analysis or code. But it turns out PoreFlow has an unusual alternative definition, and it ends up being the default definition that's shown below here. And when we ended up going through the right code-to-code benchmarking exercise, we identified this difference in retardation coefficient, and it showed up in some of the plots there, for example, on the right, where you see the circles which represent PoreFlow compared to the benchmarking alternative. You see slower release breakthrough curves, so reflecting a higher retardation coefficient. So when we pulled the thread on this, how did this happen? Well, first of all, we realized all of our QA testing was only done with problems where the medium was fully saturated. So as you can tell in these two expressions, if you're fully saturated, they actually reduce to the same value. So our testing suite was not adequate to identify this problem. We did discover it through not through a software QA exercise, but we moved on to the next stage of doing some code-to-code benchmarking. That's where that identified the issue. So then we go back to the documentation. Well, basically to its credit, the PoreFlow developers did document their definition of retardation coefficient, but it was certainly not called out that it was different than what most other people would define it. So that's a case where I would say it was maybe obscurely documented, and certainly I felt like the developer should have called that to the attention of a user, because it was easy to if you're just looking at long lists, sets of equations, you're not necessarily going to pick it up. Okay, next slide. Okay, so now I want to move on to more of this idea of quality control as opposed to quality assurance. So when we're talking about verifying an overall model, this is where I think quality control techniques come to the forefront. So the basic idea here of quality control is, rather than trying to check something once and trusting it into the future, the idea here is we need to check every time. So even though we may have a code that's undergone a QA process and it's been vetted for future use, all these other pieces of the model, which tend to be custom elements. Every model is different. Every analysis is different, has its own custom elements. So they require basically checking every time. Okay, so what lessons I've learned when we talk about verifying an overall model, I think this is fairly well documented in the literature at this point. But the greatest risk to a decision is a flawed conceptual model before we've even thought about running a code or identifying inputs to a code. And then again, if we talk about, as I indicated before, when we talk about software, I've seen more issues with problems with documentation than the code itself. A similar thing with models. I've experienced personally more problems with inputs to codes than the code itself. So the error tends to be in the input, not the code, as long as we're working with a fairly well-established and vetted code. So how do we root these things out? Obviously, independent and thorough technical reviews is critical for an analysis. And I would even say probably the best way to vet a model is to have an independent team developing a separate model. If I were a PA manager and had $1 million budget, I'd be sorely tempted to split my budget in half and have an East Coast team and a West Coast team, and not tell them about each other and have them work independently for a year and come back with their answers. And I think it would be very enlightening to see what that result would be, because you'd have independent development all the way from conceptual model down to raw results. Okay, so I've got some examples here of what I mean by quality assurance. So next slide. Okay, so this is one. This is a QC applied to a particular groundwater flow model at the Savannah River site. So the kind of just to set things up here, imagine you go out to your mailbox or you go to your doorstep one day and there's the UPS package, and you open it up and here's a groundwater flow model, velocity field and hydraulic head field. Somebody has basically presented you the results of a groundwater flow simulation. The question is, you don't know how this model was created. I mean, it could have been done by your crack national lab, or it could have been the result of taking a computer and keyboard into the zoo and putting in the monkey cage and letting them type away, and here's what came out. Okay, so the question is, I don't know whether I used a QA code or not, or how it was created. Is there a way I can verify that this is a valid model? The results are valid. And so in this particular example I was involved with, we went through a number of QC exercises on here. So we're not going to credit anything that happened before we got this model results. We want to directly vet the results. So what did we do? We went through went cell by cell and calculated the mass balance. So if it's a steady state mass or steady state flow simulation, the mass balance across all six faces of a computational cell should be 0. So we confirmed that, as well as that mass was confirmed on the overall domain. And then we also, we claim we're honoring Darcy's law. So we went cell by cell and looked at every face between two computational cells, looked at the head difference, looked at the reported flow, and said, does this satisfy? Well, and also looked at the conductivity we said was at that location. We said, does that satisfy Darcy's law? And then we obviously did the other parts of let's go and compare the simulated head to the measured heads and stream-based flows and all that. And so we were able to go through this sort of QC exercise to validate or verify this model. Okay, I've got a couple more examples here. Next slide. And these are basically, actually, Hee-Ho Park, I think, spoke exactly to this issue in his presentation, where he noted that typically typical analysis has a voluminous amount of input. It's all in a particular format that supports maybe the simulation code, and there's a need to unless you want to wade through a million lines of code and have to know all the nuances of code input, it's very valuable to have an alternative, more concise, efficient summary of the key inputs to the model that really any reviewer can look at. And so here's an example. This is in table form, and let's go to the next slide. Kind of basically the same kind of information in graphical form, but as a QC measure in some of our pore flow based modeling at Savannah River, what we do is we have a process that creates pore flow input files, and these can be thousands of lines long, but it'd be a very tedious thing to go through and to verify that all those inputs are correct. So what we've created is what I would call a QC tool that doesn't know anything about how a pore flow input deck is created. It just goes directly to the pore flow input deck, extracts all the key things that we care about, or the most important things out of the input deck, and creates summary plots and tables so that you can very quickly visually or through in a table form verify that all the property changes through time are what you are consistent with your concept or your high level specification for that scenario or modeling case. And this has been very helpful to root out errors because it allows multiple people to do checking who don't have to be, for example, an expert with pore flow. Okay, next slide. Okay, this is just another kind of example pointing to some code-to-code benchmarking. This is comparing an abstracted gold sim model to pore flow multidimensional numerical model. Now, we don't expect exact agreement here with between these two codes because, in fairness, the gold sim representation is simplified and abstracted. But the point is, I've just pulled out 3 different nuclides here that have different signatures to their release curves, and you can see that both codes are producing the similar signatures, and I'm not showing any disconnects here, but we've gone through this process and found it to be very helpful to do these types of code-to-code verification or comparisons to root out problems between the 2 different modeling teams. Okay, next slide. Okay, so I've kind of drawn a distinction between QA and QC techniques and give you some examples, and now just want to talk a little bit about what are the risks of applying these 2 different techniques, and what are some remedies. So if we talk about software QA, the basic risks are assuming that there was adequate testing done on the software that covered the full range of its capabilities or input ranges, and or even if we want to even go beyond that, assuming without a lot of thought that the model is already a valid representation or a valid analog of physical reality. And so if we kind of put those 2 things together, I mean the core risk is to assume that even if I have good input, I may not always or even ever have valid output in the sense of it matching reality. Okay, so some of the remedies, in my mind, it's key to, even if I'm using a QA'd code, a qualified code, it's still important to apply some level of QC techniques to the output. In other words, you should at least look at all the any output that comes out of the code. Just look good, just makes sense, even if I am using a qualified code. And again, as I pointed out earlier, code-to-code benchmarking and obviously comparisons to prototypic experiments, field data, natural analogs, that's highly valuable to vetting and overall analysis. Okay, so next slide. Okay, so Albert Einstein had this to say once, an experiment is something everybody believes except the person who made it. Yet a theory is something nobody believes except the person who made it. So next slide. I think if we were to apply this to risk and performance assessment modelers, we could maybe modify that second statement. And so, you know, a model is something nobody believes except the modeler who developed it. And I think what I'm trying to get at here is, I think modelers have a natural tendency to be a little overconfident in their prediction ability. The little subtitle here is too small for you to read. What it says under this overconfidence is that it's defined to be overflowing optimism colliding with true life experience. And so, you know, basically what I'm getting at is, as John aptly pointed out earlier, you know, we modelers live in a fantasy world. And if we don't always sort of keep that in the forefront and, you know, realize that and make a conscious effort to tie what we're doing back to physical reality, then that creates a risk that we will have overconfidence in our simulation and prediction capabilities. Okay, next slide. Okay, so let's look at what are some of the risks and remedies associated with quality control type techniques. Well, you know, the personal experience is you know, I'm typically using sort of little scripts and tools, software tools that I'll do just for one specific application, and of course I check the output of that tool to, you know, make sure the output, you know, is a valid output. But the next time I come around, I need to do something similar. I'm sometimes tempted to use that tool that's not been qualified or thoroughly vetted, and I'll go and use it and just assume that the output was right. So but what I'm getting at here is, you know, the basic thing we need to guard against in QC techniques is making sure we don't forget the obligation to check every time. So if we're not using a qualified code or analysis or tools, then, you know, we got to always remember we're obligated to check every time, ensure every output, every use is a valid one. Okay, so the next slide is just some summary. So you know, the basic points here are models are more than codes. Therefore, model QA or model verification is more than code QA. You know, QC techniques, that's, you know, basically where you're checking the product every time. That's a necessary complement to code QA, where that's the components of the analysis you hope to check once and then use in the future many times without checking. Again, modelers tend to be a little overconfident in their software tools and conceptual models. So channeling Albert Einstein again in the lower right, the important thing is to never stop questioning whether your analysis is a valid representation of reality, whether you've got good inputs, whether you've executed the whole process correctly. And so, you know, the key things to me in quality, ensuring quality in your risk or performance assessment product, you know, number one is data, experimental data, lab data, field observations, whatever. Independent modeling efforts, you know, code-to-code benchmarking or model-to-model or analysis-to-analysis benchmarking. Thought we had some great examples of that in day one with the oversight functions provided by, say, the NRC and other regulators doing their own independent analyses to vet that against the contractor or the facility analysis. And again, it ultimately comes down to it's always valuable to have on your team a skeptical, maybe grumpy, experienced, and dedicated reviewer who's willing to put in the time and effort to pull the thread hard on your analysis. So I kind of purposely didn't try to use up my whole 45 minutes with my own experiences because I really feel like there's some input that others could have. So I'll invite any questions and maybe better yet, any other lessons learned from the crowd here that could be shared with the community.
Thank you, Greg. Well, anybody responding to Greg's invitation to share your experience? I see Paul coming up.
Right. Thanks, Greg. One other comment or thought that something that we regard essentially as a QA tool as well as many other things is sensitivity analysis. you add that to the list, and the sensitivity analysis will reveal things in your code or in your program or your model that maybe you haven't seen for other reasons. So, I mean, we recently discovered that we had oscillations going on in a time series and wondered why the heck that was happening. But it was a sensitivity analysis that first revealed that we had a problem.
Yeah, that's a great thought. So I think the idea is that the more you exercise your code and its capabilities and over the range of parameters you'll see behavior and signatures that may or may not look right to you, and that's a good point of entry to understand how the model is behaving.
Yeah, and I guess I should clarify, that's a global sensitivity analysis on a fully probabilistic model where you can actually see everything that's going on.
Okay. Okay, great.
Kevin, also, go ahead.
George Alexander, NRC. Thank you, Greg. I enjoyed your presentation. A couple things just to echo the same things that you pointed out. I think conceptual model uncertainty can't be overstated. I think your East and West Coast teams might mutiny against you with the differences that they might get in their results. But I think that's important to understand. Just because it's difficult doesn't mean we don't need to look at it. And the second point is user error. I remember in grad school when I finally had the ability to use a geochemist workbench, I was excited thinking that was going to solve all my problems. And I didn't have to worry about any of everything that goes on behind the scenes. And an astute colleague of mine pointed out to me, if you can't do the calculations by hand, you need to be very careful in relying on a code or a model, because it's very difficult to understand everything that goes into those unless you know how to do them by hand. So I think there's a big challenge related to user error, and ongoing training I think is very important.
Yeah, that's a great point. And I'm actually in the middle of reviewing a PA document from Hanford that's based on the geochemist workbench. So they went through a lot of sophisticated geochemical equilibrium modeling. But what really struck me in their report is they saw certain behavior in the output results, and then they were able to go back to the underlying equations, make some simplifications, and create some some semi-quantitative, simpler analytic solutions to the problem, and basically show that the trends that they were seeing in the data were exactly what you would expect if you can go back to the underlying equations. And to me, that's a great example of making sure that you do enough, you can understand enough of what the code is doing just from your own concepts, and maybe doing simpler test problems and analytic solutions that you're not running in the dark that way.
Kevin Brown, Vanderbilt. Just a couple things. One is vernacular. We often run into this issue of what is verification, what is validation, what is calibration, and I ran into one recently talking to Bechtel, checking versus verification. So sometimes vernacular, I think Matt was talking about, people were talking across each other as what a risk assessment meant. Often we're talking across each other what verification means, what's calibrated, what's verified, what's validated. So I think that's going to come out in the panel, but that's very important, I think. Yeah,
I actually thought about starting off this talk with a list of definitions, but I decided there doesn't seem to be any standard terminology, and I wasn't even going to open that can of worms. I said I'm just going to tell you what I mean by QC and QA, and that's a great point, though. It's
there's a paper by Conocal that I always like. That the title is "Groundwater Models Cannot Be Validated," but he has a very nice layout of calibration versus verification versus validation. Yeah. And I think you've been in meetings. I've been in meetings with DOE, and I was like, "We're validating," and they mean, well, that's meeting performance requirements. I'm like, no, that's not what I mean. Or it's, this whole code verification versus checking thing with an engineering calc came up just the other day in the PJM mixing thing. So it keeps coming up that we don't have these standard definitions.
Yeah, that's unfortunate.
And then kind of how not to do things. Back when we were starting up DOPF, I was writing a bunch of Lisp code to say, are we making quality glass? And right before we decided to start it up, they said, we need an independent check on this code. And we spent 10 years writing 20,000 lines of Lisp code, and they were like, we need an independent calc. Who can we have do this? Well, Kevin, you understand. I was like, no, I wrote the code. So I spent 8 days writing 12,000 lines of Fortran to verify my own code, and then guess what? 3 bugs showed up in both. Amazing how that happens. Yeah. So how not to do
Thank you.
I'd like to add what Kevin has just mentioned. I think GAO audit that I kind of alluded to in my opening presentation also pointed out the same thing, that there is a need across the complex for some clarification about the guidance. So that's why we are in the process of working the guidance. Hopefully that will help to clarify some, at least the terminology part. You mentioned earlier about the need to to benchmark models with other models, perhaps. Just for information sharing with this group, IEA has focused on that area for a number of years, actually for a good 20, 25 years, starting with Introva. Maybe Matt Kozak was involved in some of the earlier effort. So the newest phase of that project is called Moderia, Modeling and Data for Radiological Impact Analysis. So that phase 2 for that project is going to kick off in the end of October. I will share the information when we pick up, the recent development in that group. I was asked to co-chair or chair the first group on risk assessment and decision analysis. So it'll be interesting to see what happens. I do have a question for you. Maybe we can defer this to the panel discussion if we're running out of time. But often a question has come up is, the level of qualification that is required to support, say, remediation work versus long-term disposal assessment. What's your take on that? Is there some kind of gradation that we can exercise, on one project versus the other, given the different intended use of models?
Yeah, that's. I don't know if I can give you any a super specific answer there. Just my general thoughts are, I think it makes sense to have a graded approach to your quality assurance protocols and standards, depending on the significance of the decision and the analysis. So I think there's definitely room for a graded approach to how you go about doing your QA. Me as an analyst, I typically don't own that decision. It's the owner of the performance assessment document or analysis. I'm sort of a service provider, so I personally, don't take any position one way or the other on those things myself personally. So I'm happy to adopt whatever level of rigor or efficiency that the funding agency or the owner of the analysis wants. So.
But come on.
I may be dodging a little bit, but that's sort of that's where I'm at personally.
Let me challenge you a little bit on that, because you are represented from the national labs. The labs are the crown jewel of our complex. You're the brain for our business. So we can pick up this topic maybe during the panel discussion. I'd really like to have some thoughts maybe from each of you, as I said, we're moving forward with development of guidance. That's one aspect that I think we collectively need to address.
Yeah, maybe I didn't state my position too accurate. I mean, certainly for a regulatory document that tends to lead you to the higher levels of quality assurance. But sometimes I'm doing just scoping analyses that don't have any particular input to a performance assessment document. So. It all depends on the level of modeling I'm doing, what the end result is. But I'm not trying to minimize the need for quality assurance procedures and protocols, when we get to the regulatory level.
All right. Any other questions? Yeah, John.
You were asking for experiences, so I just have one experience I'd like to share. I actually do more than modeling. There was a project where we were engaged by EPA to do statistical analyses on data buoy data from National Oceanic and Atmospheric Administration. There are hundreds of buoys that are out floating in the ocean, sending in data all the time, and they wanted to do that. And they wanted the code to be written in Java, and so I was writing that code, but we decided up front, how are we going to be able to determine this is giving us the proper results and avoid coding errors and things like that. So we decided to do the same. We weren't on East Coast, West Coast. We were in the same office, but we coded the project up on two completely independent platforms. So I was working in Java, and we had a statistician do the same work using SAS. And we're working from the same data sets and producing the same code. And actually, we found a number of errors in each other's code and worked it all out. And finally, we agreed on, no, this is how it should be done. And then the surprise result, or maybe not the surprise result if you've worked with data sets, was there were lots of errors in the data set. And we were able to flag all these errors in the data set. But we were confident that our codes were working right. And then the next step would have been to go back to them and say, by the way, Noah, we have all these, we found all these errors in your data set. Would you like, now we have these codes that can you identify them? Would you like us to go identify that? But the idea of developing things on two completely independent platforms by two independent people is a great way, if you can manage to do it, it's a great way to, for QA anyway, and QC, I guess, too.
Yeah, I think your last point is a great one. It's it is expensive. It does require time and therefore money. But if your decision, if your analysis is critical, it's can be certainly worth that effort.
Any other questions for Greg? If not, thank you again. Well, I think we'll break out for lunch a little earlier. Hopefully that will give you a little more time. Please come back by 1 o'clock. We'll start at 1. Okay, thank you.